Okay, good morning. Let's start our discussion of phase transitions. Now, we have studied up to now the one cause of interparticle interactions, which is the correlations, that in space the particles are ordering in some sense. So their positions are correlated because of interactions. And of course, another result of these interactions is the most important phase transitions. And let us start studying this. It's extremely important. Could be a subject of a different course, of course, another course, the whole semester course. It is a very wide subject. I will give you in this lecture very basic description, the parameters of phase transitions. When we talk about phase transitions, of course we have in mind phenomena like condensation of gases. This is a phase transition from gas to liquid. And melting of solids, it is a phase transition from a solid to liquid. Ferromagnetism is also a phase transition from a non-magnetic state to a very strong magnetic state. And superconductivity, for example, is a result of the ordinary superconductivity, is a result of pairing of electrons as a result of electron-phonon interaction, isn't it? So there are lots of transitions like this. The only exception to the rule that we need interactions for phase transitions is the Bose-Einstein condensation, as you know. There we had the transition of particles into a state where the ground state is occupied macroscopically without any interactions between particles. Now, one important thing, the very first thing that we have to note in all these phase transitions, the thermodynamic quantities kind of at the critical point diverges. There are some singularities. So let's note that. That's the most important fact. So discontinuities or singularities in thermodynamic functions at critical point. Or transition point can be a critical temperature, for example. At a critical temperature, you start seeing these singularities in thermodynamic functions. Of course, at those singularities, at those transition points, particles are interacting with each other strongly, and there's a cooperative effect. The whole of the particles are taking a role in this transition. Extremely important. Now, let me try to describe the most important things about phase transitions in a systematic manner. For example, one thing is the phase diagrams. We have to know this, that there are we can have phase diagrams for all materials where you have different types of phases. For example, in a PVT system, let's show this as an example. So this is a bit different than a magnetic system, isn't it? Because in these systems, pressure, volume, and temperature is enough to decide on the state of the system. Let's look at a possible phase diagram. Here is a possibility. A bit difficult to draw these correctly. Here is a possible phase diagram where the axes are showing pressure, volume, and temperature. And of course, if the pressure and temperature are so that the gas can exist, gas form of the material, this part of the diagram shows that this system is in the gas phase. Well, if you increase pressure and lower the temperature, of course, it goes into a solid phase with more pressure and temperature, lowering. Well, this is solid and gas can coexist together, and that part is liquid and gas can coexist together. Here, solid and liquid can coexist together. Okay? So that is kind of a phase diagram. Give me the pressure, volume, and temperature. I'll tell you in what phase the system is in, isn't it? So that's a phase diagram. Usually it is not given as three-dimensional figures projected into two dimensions, but we can have projections. For example, you can look at this as a pressure temperature cross-section. Okay, so cut this in the pressure temperature configuration. Then you have the following thing. You might have the following thing. Here you have solid. This is triple point. This is critical point. This is gas, and that is liquid. So you probably see this type of diagram for a phase transition, phase diagram. Now, of course, if you start at a certain temperature, keep it constant, increase the pressure, you may reach that line, isn't it? Separating solid from gas. Or at a higher temperature, you may reach that line by increasing pressure, where you reach a boundary between liquid and gas. Along these curves, liquid and gas phases coexist together. So those are lines of coexistence of phases, isn't it? Here, liquid and gas. Here, solid and liquid. Here, gas and solid can coexist together. Extremely important to know that there are these phase diagrams for almost any material you want. You can check the phase diagram, corresponding phase diagram for the material. Now, let me show you why it is important. For example, the slope of this is extremely important. Slope of solid-liquid separation or coexistence curve, well, you can call it the solidus or liquidus curves, lines. Now, this is a positive What is positive there in that curve? Slope, isn't it? Slope is positive. But in water, it is negative. So, in water, that thing is going like this. Is there any importance of that? Being positive or negative? What? Now, this is the result, but this is the cause of you falling on ice, or you are able to ski, isn't it? No, you don't know yet. The reason is, if you are at that temperature in a cold day, when you increase the pressure, what happens is that you are going from solid to liquid phase, isn't it? That means when you step on the ice, down below your feet, you create liquid. That's the reason why you are falling down. Huh? That's the reason why you can ski. Otherwise, if you are dealing on a material like this, on Earth, for example, if you increase the pressure, you go from liquid to solid phase. Nothing happens there. You can walk on that material very easily, isn't it? So it is kind of important to look into details of the phase diagram to see what it tells you about the state of the system, the property of that specific material. In a ferromagnetic system, we have a different phase diagram. ferromagnetic, systems, you know, these are very strong magnets. Here you have a phase diagram like this. So there is a critical temperature on the temperature scale. This is magnetization. All of a sudden, you end up with a magnetization. This is the magnetic field. So you have something like this. So that is also a phase diagram. You see above TC there is no magnetization, but below it you have a magnetization appearing at temperatures below the critical temperature. So you have a phase transition from a non-magnetic state to a magnetic state, even in the absence of the magnetic field, even when magnetic field is zero. So the systems may be different, but phases it might have can be shown in a diagram, which we call phase diagram. So we have to understand their presence. We can go to the library and find lots of phase diagrams for different materials. Do you have any questions with this? The second thing I want to mention is the symmetry breaking in phase transitions. Now we know how to get the phase transitions. We know the phase diagram of the material. We know what to do with temperature, pressure. In the case of magnetism, magnetic field and temperature, to go into a phase we like. Here, the second concept is the symmetry breaking. Have you heard of this concept before? Huh? Did you hear about this? What is that? Now, highest temperatures gives you what? At highest temperatures, the systems are disordered, isn't it? Because temperature, in the case of magnetism, for example, is the killing parameter of magnetism, isn't it? It kills order, and it introduces disorder into the system. So, at highest temperatures, systems are disordered. Now, a disordered state is a state with highest symmetry. Why? Well, if you talk about a magnetic system, again, all the spins are showing in different directions. No direction is chosen, so all the directions are equivalent, isn't it? So it is really very good symmetry in the system. Now, if you create magnetism, like in ferromagnetic transition, what's happening? All of them are showing in the same direction, the perfect magnetism, let's say. Then one direction is chosen, is different than any other direction, isn't it? So rotational symmetry is broken, for example. There's no symmetry anymore. Huh? So it is the symmetry breaking we are talking about. Let me tell you what is broken in different transitions. Symmetry is broken. Of course, in a ferromagnetic system, it is rotational symmetry is broken. Isn't it? Because you choose one direction to be different than other directions by magnetizing the system. All of the spins in the same direction, that direction must be different than any other direction. So you have broken the rotational symmetry of the space. In a crystal, for example, what is broken? Crystal is a state in which particles are sitting at certain lattice points. The translational symmetry is broken, isn't it? Not all translations are allowed to give you the same symmetry. Only a translation taking you from one crystal point to another gives you the same symmetry, isn't it? So certain translations give you the symmetry. So it is translational symmetry which is broken. Well, let ferromagnet be told that what is ferroelectric? Ferroelectric is like a spin system, but instead of spins, you have the electric dipoles. So you can order electric dipoles by applying an electric field instead of a magnetic field, isn't it? So it is inversion symmetry which is broken. Superfluid it is gauge symmetry which is broken. You have to learn about symmetries to understand what symmetry is broken. But when you have a transition, you have a symmetry broken. That's an important thing, and the best example is the ferromagnet, where the rotational symmetry is broken when you magnetize a material. Do you have any questions with this concept of symmetry breaking? Huh? Is it understood? Okay. Now let's go to the third important thing about phase transitions. It is an important feature, which is the order of the phase transition. I'm giving only the most important things. Well, usually when you read an article about phase transition, you see an underlying concept of first order phase transition or second order phase transition, etc. There is an order of the phase transition. Now, let me introduce the earlier version of the order, the definition of order. Then I will give you today's version. Today we have only a first order or a second order phase transition, okay? But earlier description is due to Gibbs, Paul Ehrenfest, concentrating on the Gibbs energy, free energy. Okay, order of phase transition. Now, Paul Ehrenfest is the well, you heard his name in quantum mechanics, of course. Huh? Classical limit of quantum mechanics. Paul Ehrenfest also discussed the orders by noting that when two phases coexist, okay, the important thing is they have common temperature and common pressure and common Gibbs free energy. Common Gibbs free energy comes from the fact that the chemical potential is Gibbs free energy per particle. So common Gibbs free energy means common chemical potentials, aren't they? That means no particle exchange from one phase to another. So it is normal that the temperatures must be the same so that there's no heat transfer from one phase to another. Pressures must be the same. There's no motion of the separating membrane, let's say. And the chemical potentials, that means the Gibbs free energies must be the same. So let's look at the Gibbs free energy as a function of inverse temperature or temperature. Now, one phase may have this line, phase 1. Second phase may have this line, phase 2, alone. When they coexist together, the actual Gibbs free energy could be this, isn't it? There's a kink in the actual Gibbs free energy. Huh? So, king. So Paul Ehrenfest decided on the order of the phase transition by looking at the king, the property of that king in the Gibbs free energy. It says transition is nth order well, when you look at the derivative of the Gibbs free energy as a function of temperature, this derivative gives you the entropy. So depending on discontinuity in the GDT, then that thing comes out. Transition is nth order if the nth derivative is discontinuous. So, look at the derivative of the Gibbs free energy. Which derivative is discontinuous? Discover that. If it is first derivative, then it is a first order phase transition. If the second derivative is discontinuous, it is the second order phase transition. Huh? Very understandable. Using that king in G function. The first derivative gives the entropy. If the entropy is discontinuous, then it is a first order phase transition, isn't it? So that is the old definition of order of the phase transition. Now, nowadays, as I told you, there are only first and second order phase transitions. So whether the entropy is continuous or discontinuous, that's enough to decide on the order. So nowadays, it is first order phase transition or second order phase transition. That means discontinuous and continuous phase transitions. Discontinuous or continuous phase transitions. That's what we have. Is this okay with the order of the phase transition? Do you have any questions? Huh? So, first order phase transitions if there's discontinuity, and second order if there's no discontinuity, a continuous phase transition. There is another way of defining order. It is the order parameter in a phase transition. Order parameter. That's also another important thing. We are going to discuss it further as we go into the problem. Order parameter. That's extremely important. Well, that's a modern general theory of phase transitions, started with Landau. His contribution is quite important. 1930s. And this language is applicable to all phase transitions. The order parameters, well, in all phase transitions, at the phase transition point, critical point, something goes to zero. Okay? That something is the order parameter. Let's see what goes to zero at different phase transitions. Now, on warming a ferromagnet, what goes to zero? Something goes to zero. If you warm a ferromagnet, what goes to zero? Increase the temperature, you kill something. What is it? Ferromagnetism. It is the magnetization, isn't it, that goes to zero. If you warm it, it is the magnetization goes to zero. So, extremely important. At Tc, the critical temperature, if you go over it, it goes to zero. You don't have any magnetic state anymore. Remember the phase diagram? If you cross Tc, there's no magnetization. So magnetization goes to zero means magnetization can be taken as the order parameter for that system. Well, let's take unwarming means increasing temperature, a fluid if you do it along the coexistence curve, what happens? What goes to zero at the phase transition point? Liquid goes to a gas, isn't it? Goes into a gas. What goes to zero? Well, it is the density difference goes to zero, isn't it? That's unwarming a fluid difference between liquid and gas densities. Goes to zero at Tc. You go from one into another, okay? So, if you warm a superconductor or superfluid, it is superfluid density that goes to zero. that goes to 0 at Tc, you don't have any more superfluid phase if you increase the temperature above the critical temperature. So some quantity goes to 0 at the critical point. When there is a phase transition, that quantity that goes to 0 is the order parameter of that system. That's the Landau's definition. And this something is the order parameter. Which will be shown by phi. Let me give you some examples of the order parameter. Okay. In a ferromagnet, what is it? What was going to 0? Huh? Magnetization. So order parameter for a ferromagnet is magnetization. So system order parameter that goes to 0 at the transition point when you increase the temperature, for example, ferromagnet and it is magnetization that goes to 0. Americans call this Z, isn't it? USA and UK are two countries divided by the same language. They have some differences. Magnetization is a vector, so that is the order parameter. And for ferroelectric, what goes to 0 is polarization, isn't it? In that case, when you put an electric field, you polarize the dipoles, electric dipoles, so polarization is also a vector. In a fluid, we talked about where it is the density difference and critical density that goes to 0. This is a real number, a real scalar. Okay, which is the order parameter. Superconductor it is the pair wave function that goes to 0. Psi superconducting state. In an Ising model, it is the Ising magnetization. Okay? So you can increase this list, and why don't you do that? By checking your book. So order of the transition depends on the order parameter. Is it continuous or discontinuous? Order parameter as a function of temperature. If it goes like this and it is discontinuous, okay, discontinuous, then it is first order phase transition. Huh? If it is continuous, you have second order phase transition. If your order parameter goes continuously, this is second order. And it is continuous phase transition. So that's it. That's another way of classifying the phase transitions. Is that okay? The order of the phase transition? These are the most important thing about the phase transitions. Okay, there's one more important thing. Okay, lots of important things, but I'm telling you the most important ones. Critical exponents. I said something diverges at the critical point. There are some singularities. But how is important. How certain quantities diverge is extremely important. And we define this by critical exponents in a phase transition. Another concept, important concept, is critical exponents. What was the number? 4. Critical exponents. Extremely important. We have to understand a transition in terms of its critical exponents, because, well, this is telling us how the thermodynamic functions are diverging or showing these singularities at the critical point. Now, let's define a reduced temperature to see the way divergences appear. Let's call it small t instead of capital, as we are using for temperature. This is defined by difference between the real temperature and the critical temperature. It goes to 0 at the critical temperature, isn't it? When T is Tc, this reduced temperature is 0. So we can define the singularities in terms of this reduced temperature. Now, usually we are going to talk about heat capacity, and it diverges like T to the minus alpha. So alpha is the critical exponent corresponding to heat capacity. So it is heat capacity critical exponent. These are definitions. So when somebody tells us something about alpha, we have to know he's talking about the heat capacity. See, T to the minus alpha means 1 over T minus Tc, isn't it, to the power alpha. So at T equals Tc, it diverges. There's a singularity. So that is alpha for heat capacity. There is one for order parameter. Order parameter For example, in ferromagnetism, magnetization goes like T to the beta. Beta is for the order parameter. At T equal Tc, it goes to 0, isn't it? It becomes 0. It is not negative in that case. Susceptibility well, this is the quantity that tells you how easy or difficult to magnetize the system in the case of magnetization. That is given a critical exponent gamma, so alpha, beta, gamma, for heat capacity, order parameter, and susceptibility. They may change for different systems, but alpha, beta, gamma is given like that. Then there's equation of state. Critical exponent at Tc, critical temperature. For ferromagnetic system, it is magnetization that goes like the magnetic field to the power 1 over delta. So this is another equation of state, critical exponent, alpha, beta, gamma, delta. Well, if we want to give examples from the ferromagnetism, here is the possible look of these quantities at the critical point. Let's start with heat capacity. Well, examples are from the ferromagnetism. C as a function of the temperature. It goes like T minus alpha. Okay. Magnetization goes like the second quantity goes like this, almost like that. Magnetization as a function of temperature. So above a critical temperature, Tc, there is no magnetization. The system is disordered completely. Spins are showing in all directions. But at the critical temperature, below the critical temperature, system starts to be magnetized, develops a magnetization. Susceptibility is something like this. There is a divergence in susceptibility, chi. Well, you can look at these as a function of interaction parameter too, not only temperature, but interactions are causing ferromagnetism, spin-spin interactions. So there is magnetism even in the absence of applied magnetic field. So if we are talking about the effect of interactions, so that's it. Equation of state also behaves a little bit differently. There is an inflection. This is m at t equals tc. as a function of applied magnetic field. So there is magnetization even at zero magnetic field. That's ferromagnetism. So these are the four basic critical exponents, but there are more. For example, correlation function we have studied in the last lecture has a critical exponent. Oh, I am carried away with the... But you are still telling me nothing. You have to tell me, sir, the time is up. Something like this. I will continue lecturing in this nice subject for a long time, but I have to stop, give a break. Okay.